for the clear presentation. We move on to the next and last speaker of this morning session, Benjamin Basso from the École Normale Supérieure.
Okay, so.
Oops.
Thank you. Okay. Well, I'd like to start by thanking the organizer for inviting me and for organizing this nice conference in Budapest. It's always a pleasure to come back. And what I want to say today is based on the paper that we published recently on the archive with Alessandro Giorgudis, who is a postdoc at Nordita, and my student Arturo Clemenchuk-Suero. So they are both here, and there was also a poster by Arturo related to the topic. So it has to do with trying to calculate the structural constant of single trace operator in n equals 4, our favorite theory. And I'd like to start with an apologize to some of you who were there last year, because what I'm going to say is very much related to what I said last year. So sorry for the overlap. But what we have now, I think, is much more interesting and much more promising than what we had previously. And this is the reason why it's, I think it's worthwhile to present it again. So it's a bit like a V2 of last year's talk. Okay, so the main question that was driving this project was trying to understand what exactly controls structural constants of single trace operators. So how can we calculate them at finite coupling in the planar limit, using integrability. So what we have currently is a description, a very, very powerful description for the spectrum of scaling dimensions of single trace operator. Which is for which we have overwhelming evidence. I don't think we have anything like a proof from the very first principle of the theory, or from the Lagrangian or whatever. But there is a construction which is extremely restrictive and constrained. And perhaps some people could argue that it's a unique description once you take into account every possible constraint. And in its current incarnation, its best form is probably given by what is called the quantum spectral curve, which was a kind of upgrading to begin with of the thermodynamic bed ansatz, which has the advantage that it allows one to deal with operator of any sort, not just some specific operators that we like more than the other, and also make all symmetries manifest. So there is a freedom that we get with this quantum spectral curve that we did not have with the TBA before. And of course, it is expected to be complete with respect to the coupling, meaning that it should, in principle, give us the answer at any value of the finite coupling, at any value of the coupling of the theory. So for the structural constant, or for more complicated correlation function, higher point function, or there is a growing evidence, perhaps not as overwhelming as for the spectrum of scaling dimension, or at least perhaps not as well tested as for the spectrum of scaling dimension, that we can describe them at finite coupling again using integrability by means of the hexagon formalism. There is also indication that we can use it to calculate in 1/n expansion, so to go towards the loop correction, the G-string loop correction using this method. But, well, as I say, it's growing evidence, but it's not yet a complete description. There is some obstacles on the way, and we could say that the hexagon is describing very well the geometry of this planar surface that we are trying to describe, but perhaps not so well the punctures themselves that we are trying to put on this geometry. and which we expect or we believe are, on the other hand, extremely well controlled by or described by the TBA or the QSC description. Mm-hmm. So it's not a counter evidence. You're saying that it's not a complete. From the QSC, you mean? Yeah. Yes. 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 So you mean in 1 over n? You mean when you expand further in 1 over n? Or? Ah, okay. No, I was not aware of this tension. So you are referring, so this is some number theoretical properties of the coefficient. Yeah. So there is a proof and by Dima and collaborators about what type of object you will produce for the scaling dimension. And you are saying that there could be some tension at higher loops with some Feynman diagrams. Okay, I was actually not aware of this. So, well. Yeah, so I can just repeat it my way. Maybe I think I understood the point. So it's just it's a possible tension between the prediction one can make from the QSC as regards the loop coefficient of the scaling dimension, which were observed and proved by Dima and friends to be essentially multiple. Some Riemann zeta values or generalizations thereof. And there is, on the other hand, some claims or expectation from just Feynman diagrams analysis that there should be some elliptic object showing up at late loop order. So if it is true, if it is so that eventually, inevitably, one would have to find some elliptic numbers in the expansion of the weak coupling expansion of scaling dimensions, then there would be a clash with the QSC, because apparently QSC does not predict that.
Sorry, but are the claims of transit round even true for 2-point functions, or just for hyperpoint functions, like a 4-point function, like a 4-point function?
Well, my understanding is that it's sort of a more a property of graphs that that there is always some graphs in some order, and then there's this general thing in graph theory that if you take some random graph in a sufficiently big graph, it will always appear as a subgraph. Once again, I'm not trying to say that I don't believe any of these evidence. I just want to point out that it's an interesting thing to explain why in n equals 4 these things don't seem to appear. That's my point.
Let's move on and
yeah.
return to
Okay,
this
thanks for the comment. So definitely we have a solution, but we don't understand it very well. So, so the question one may ask, and it has been asked previously, I think, is whether there is a unifying picture for both the spectrum and the correlation function. So something that we could perhaps be, how to say, happy to have, like, in order to describe all the quantity we care about. So it's not something that may be that urgent, actually, to combine, for instance, the TBA with the hexagon if we consider higher point function of protected operators. So there is less problem, I would say. In principle, the hexagon approach is expected to be finite and well-defined, so it's more like a technical problem. important technical problem, but the technical problem of finding a way of summing this hexagon expansion, which is quite involved. But in the case of structure constants, what is interesting is to look at non-protected operators, so the ones that carry anomalous dimension. And there it seems unavoidable, I mean, necessary to get some input from the exact wave function at some point. So the hexagon alone are not giving us that information yet completely, or not obviously. And so we need to do some sort of merging of hybridization, put together the TBA or the QSC and the hexagons to get something, perhaps something new, or perhaps just a monster, I don't know. So in this talk, I would like to give some evidence and also present a conjecture that the two paths join precisely when wrapping are becoming important for structure constants. And I would like to add also that this, this is one way of trying to merge things together, but one could try different ways, of course, and we heard Fernando earlier telling us how to proceed. And one approach that seems very powerful and inspiring some work recently with very nice results is to try to use the spectral data that one can have from the QSC and combine with crossing symmetry and the bootstrap to essentially try to find the structure constant, or at least obtain some constraint on the structure constant like the one that were derived by Fernando earlier today. So that could also be the way. I mean, we may not have to do everything within a single scheme using integrability all the way from beginning to end. Maybe we may want also to consider other options. So here's a plan for the talk. So I will essentially present the conjecture and motivate it on the way. So it's only valid for a particular class of structure constants, the simplest one we can think of, where we have two BPS operators, which are here represented by this single trace operator of complex scalar fields, which have protected anomalous dimension, so a protecting scaling dimension, so zero anomalous dimension. We take two of them, and a third one, which is a more interesting operator, which carries spin and anomalous dimension. Okay. So these are the kind of operators that we will find if we cut the 4-point functions that Fernando talked about today. Okay, so for two gravitons, if you want, protected state and one excited string. And I will describe a few checks of this conjecture in particular regime. So as I say, the idea is to start from the hexagon, try to go as far as one can this way, and eventually, when it appears necessary, provide some extra input to get a more complete picture. So the idea behind the hexagon is extremely simple. It's just amount to cutting the pair of pants that is describing the 3-point function in terms of hexagons. So for that, we draw some dashed lines that are connecting the three operators or the three strings of length L1, L2, and L here, and cut along this dashed line. So what we will get immediately, as you can see, is two hexagons, which are carrying on their edges some of the excitations that we put on the boundary. Okay, so here we have one state that is excited with some magnons on it, with momenta P1 and P2. And so these one are eventually falling on the hexagons after cutting. And each hexagon in this picture is bounded, obviously, by 3 segments of spin chain from the 3 operators, and also these 3 mirror cuts, the SYM of the pair of pans that we created by the cutting procedure. So when we say that the structure constant has something to do with hexagon, what we mean is that here this is a number, and here we should think about this hexagon as being some form factors or representing some operator of sort that has the possibility of producing particle asymptotically on its edges. Okay? And these particles are just the magnons coming from the excited operator, or also some fluctuations that we may have when cutting on this mirror cut here. Okay? So this one, it describes the fluctuation of this open string that is stretching between 2 points or between 2 operators. Okay. So in general, this hexagon form factor are complicated function of all the quantum numbers and rapidities of all these excitations that we may have on the boundary. Okay. But the good thing about them is that they are form factors, like defined asymptotically in a very large volume. So we have a lot of handles on them. We can write some bootstraps, some bootstrap equations, and also propose a solution at finite coupling. So it's a piece of information that we think we have, and we can use now to reconstruct the structure constant. So the procedure for getting back the pair of points out of the hexagon is also in principle very clear. What we have to do is essentially glue at the place where we cut. And this gluing, we think, should be achieved by essentially summing over all the possible states of the open string. Okay, so this is the idea that when we try to glue things together quantum mechanically, when we have an Hilbert space representation, we should just insert the resolution of the identity. And if we sum over everything, we take into account all possibilities. And on the way, we should also pay attention to the fact that the magnons at the top here can in principle fall differently on the hexagon. They could be together on the same hexagon, or they could be distributed otherwise. And then we also have to sum over these options that we have there. Okay. So I will ignore this sum. It's not the most complicated part in the problem, and I will explain later on how it's coming back. So what we get in the end is some a bit impressive formula where we get to sum over each cut, left, right, and bottom on the figure, with certain rules and certain weights. Okay, so the sum must be inclusive, as I say, so they should take into account sum over n, which is the total number of mirror magnons that we can exchange. So they are shown here by these little arrows. Okay, so we should, oops. Okay. So we should have as many arrows. We should sum over any number of arrows here, and also give to these arrows all the quantum numbers they may carry with them. That includes integrating over rapidity u, which is parameterizing the energy of the particle that is exchanged, and also some spin. So to completely resolve the Hilbert space of this theory, we actually have to consider an infinite tower of representation of the symmetry group, which is Bizert extended SU2/2 square symmetry. And we get to consider all possible representation with spin A. Okay. And everything here is in principle known. I did not write everything explicitly, but the formula for the energy, for instance, is very well known. It's given in terms of the Zhukovskys. There's something weird with trackpad. And we also get to integrate with certain measures that we get from the formalism, from the hexagon construction. They are also relatively simple and can be written explicitly in terms of Zhukovsky variables. What is slightly more complicated is the rest, whatever is not in these first two formulas, and which is essentially capturing all the interaction between the mirror magnons in this figure and also the physical magnon at the boundary. So although more complicated, they are still completely factorized, which is something nice. And they are captured by a certain number of functions, this weight W. There is one for each channel, L, R, and B. And they can be expressed also very explicitly in terms of objects that are familiar, like SU2 transfer matrices. So I wrote here just an example of the formula that one gets, where this H is this hexagon form factor. Z here is just a collective notation for the magnon at the top here, for the excitation in the spin chain. And these TA, they are SU2 transfer matrices built out of Bizert S matrices. So they are the same object that we've seen earlier this week. So this is almost essentially it if you think in terms of the original goal of trying to apply hexagon to structure constant. At least this is the most compact representation we could find. And in principle, if one was capable of summing all of this, it will get an exact description at finite coupling, because everything is known at finite coupling. But this is a little bit too naive because of wrapping corrections. So what are they? So in the case of the hexagons, they are very closely related to to the fact that we have this term here in the integrand between the magnon u and v, which are the magnon on the left and right side of the picture. So they are controlled by this function p, which I'm not giving you, but which is very simple, and which has a double zero, so resulting in a double pole in the interaction. So in other words, these integrands are not integrable. We get some singularity, and we have to make sense of this singularity. And closely associated to this singularity are these contact term or tiny loops that we have to add to the formalism, and which are this wrapping. So pictorially, what we have to find by regularizing this interaction is a way to bring in an extra family of corrections that we are used to represent by this loop that are going around the excited operator. So these are the wrapping corrections. So this pole, in a way, is are reminding us, is a way the hexagon is reminding us that, okay, finite size correction in general are not that easy to encode. We cannot just sum over asymptotic basis of state. We also have to work harder. So schematically, or perhaps mathematically, what we are lacking is a prescription for integrating this double pole, and also a way of introducing the wrapping in the picture. I like to emphasize that we cannot just do one without the other. It will not be very consistent. And on top of that, if we change prescription, usually we redefine what we mean by wrapping, okay? Because different prescription will correspond to different contact terms, which will affect the weight that we are giving to these loops here at the top of the picture. So these are, at the cartoon level, these are exactly the same type of corrections that we have met in the past, that people met in the past in the study of the energy levels. So at least the picture are more or less the same. So one could ask or wonder why not using the TBA here? So why not starting over and trying to set up the formalism in such a way that we will eventually be able to resum this infinite series of wrapping like in the usual TBA picture? Well, the problem is that we are not calculating a free energy like a cylinder or something with, a cylinder with a boundary, and it's not immediately obvious how to set up the TBA in this case. So how do we exactly embed this geometry in a TBA setup? So until we get a better understanding of how to do TBA on any surface, I guess we'll have to proceed differently. So I'm not giving the bottom weight here because it's, it's very similar to this formula, but it's actually analytically continued to a different Riemann sheet. So I didn't want to go there yet. But thanks for the comment. I should add that here I'm a bit sloppy with the notation, and so the various arguments can live in different sheets. So depending on whether they are on the mirror or on the physical kinematics, one has to do a proper analytical continuation. So how can we search for wrapping? So there is a long way to go, which perhaps one day we will implement, I don't know, completely, which will be to start from something that we trust and we believe is totally finite and well-defined, like a 4-point function of protected operators, preferably something we can analyze using hexagons, because eventually we want to recover our hexagons. And then reduce the structure constant of interest by going to some OP limit. So that is in principle possible, and that is also something nice to do, because it will be finite and everything will be regulated physically. Okay, so there will be no. The problem with the regulator usually is that when we introduce them, sometimes we don't have full control on the way we bring them in, and that might pollute the result. That might produce some artifact in case the regulator is not properly designed. So here we will start with something that is completely finite, a 4-point function. We will just stretch the legs and eventually get out the structure constant. So that is something that can be done in principle, or one can try to do it for the first few corrections, for instance, by using the hexagonalization of 4-point function. but it's hard to carry it out all the way to the end. So we are definitely missing some appropriate collective field techniques or resummation techniques that will permit to do it systematically at any order. So, but this is giving us some data. So we can go this way if we are patient enough, and also with a little bit of guesswork sometimes, because it's not, okay, there are technical difficulties that one may want to avoid. This is giving us some data. And with this data, we can try another way, which is a lucky way to go, where whatever we get from the leading exponential correction, we try then to promote as consistently as possible to a null order formula. So that is a kind of game that we cannot play usually in the real world, but with integrable systems, there is often some sort of simplicity associated to the solution, which may be identified or recognized relatively quickly from the first corrections. So that is a hint at what could possibly happen, and using this hint, one can try something more risky to, as a null order solution. So this is what we were trying by, in summary, getting some information from for the leading correction, and then trying to make them as consistent as possible exactly, okay, by some extrapolation. So the observation that we've made first was that everything seems to stay intact. So all these factorized formulas that we had before for the hexagons, they were essentially staying the same. The only thing that was changing was that these weights that we had before, that were expressed in terms of this Beiser transfer matrices, they were kind of shifted, okay? They were modified. So they were receiving some correction, which are induced by wrapping, and which are parametrically exponentially small in the volume, but which are there if we try to get to very short volume. And what is more is that we could find some sort of natural extrapolation for this weight. So the corrections are such that two of the weight here, the left and the right weight, are obeying this simple or relatively simple relation to the y function. So here I'm assuming that the y function are given to me through the solution to the TB equation. And we are essentially trying to relate this weight, which are a bit exotic, to this y function, which are more, which are better understood. Okay. So what is a bonus, and we did not immediately recognize, but was, I mean, eventually very important for us, was to go to the transfer matrices, in fact. So if instead of trying to relate this weight to this y function by this complicated relation, perhaps the second one is more complicated than the first, and if instead we go to this parametrization of the y function in terms of the transfer matrices T, which are defined this way, then we get something which is extremely simple and very encouraging for this weight as a ratio of certain ratio of these transfer matrices that parameterize once again the solution to the spectral problem. So here the shift minus and plus are referring to shift of the rapidities in this formula. And I should add that these transfer matrices are not objects that are completely unambiguously defined. They, as you probably know, they are defined up to a gauge transformation, which leaves this ratio invariant. And in our case, for the identification to work, we had to rely on special relations that this T obeys in order to reproduce this formula here, which are gauge invariant, sorry. And this formula holds in a very particular gauge, which is this distinguished T gauge of Collier and friends. So the claim here, or the first conjecture number one, is that this is the exact solution to the problems that we are trying to solve. So eventually, if one could resum the wrapping correction, our hope, our conjecture is that one will recover exactly these transfer matrices that enter into the spectrum and nothing else. So the emerging philosophy here is that, okay, we had some asymptotic transfer matrices before, and that was good enough for the description of long operators, because they were based on this symmetry that are preserved by the very long ferromagnetic vacuum and the associated S matrix that describes the scattering of magnon on the chain. But it seems natural once one takes into account wrapping correction, such as to get short operator, that this transfer matrices get replaced by something that is somewhat more meaningful and which relates to the full symmetry algebra, which is not the subgroup that was introduced by Basso, but the full symmetry. Okay. And this is the same philosophy that we see at work for the spectrum, or that we've seen at work for the spectrum, where essentially the T function are directly connected to the symmetry algebra and eventually determine the Y function and the TBA. So if one believes that the symmetry is more important than the rest, then possibly the T function are the right starting point for this problem. And all we have to do is to deal with them and learn how to eventually reconstruct the full thing, as was done for the spectrum long ago. So here I just wanted to remind you the main defining property of this T function, which is that they obey the Hirota equation, which is a fusion relation for transfer matrices associated to different representations of the superconformal group. So this is a very nice and simple recurrence relation that involves also some shift of the rapidity parameter. And in the case that was studied for the spectrum, the T function of interest, the ones that underlie the Y function, are associated to certain infinite dimensional representation of the superconformal group. And they fill this famous T-hook domain for the various representation of the auxiliary space that one should consider. So there is an extra weight in the game. This is this bottom weight, which is kind of standing out because it's standing far away from the operator. And it is indeed a little bit different. And at first, when we play this game of trying to extrapolate results from the IR to the UV, we got it wrong. And but eventually, with this new philosophy that we adopted, we try again, and we convince ourselves that this channel, this weight can also be expressed in terms of transfer matrices. But these are not the transfer matrices that are that were used for the spectrum, at least not the ones that are related to the Y function. These are different. This is a different family of transfer matrices which are associated to finite dimensional representation of the superconformal algebra. So they are very well known in the case of spin chain, since this is usually the auxiliary space that we choose, the smallest possible representation. But in the case of the TBA and the Y system, somehow they disappear from the study, and they get replaced by this other T. But they are there in our case. And well, the simplest way to see that is actually to think a little bit more about what is this weight about and how to represent it. So here's a cartoon for this weight, in which we put the non-BPS operator at the center of the picture. And so this is the bottom channel that we unfolded. And we are placing some excitation here on the side. So if you want to think about this weight up to an overall normalization, you could say that this is just a sort of one-point function, a matrix element of this non-BPS operator. Okay. So this non-BPS operator is sandwiched between a magnon with rapidity u at the bottom and a magnon of rapidity u at the top. Okay. This is 2 minutes or 20?
No, I can just ask. Didn't you say it was a BPS?
No, so the guy with the small dots here is non-BPS.
Yes, but outside previously was BPS.
So left and right here on the leg here, it's BPS. On the side, it's BPS. In the middle, it's. I just turned the picture around. So. And what is even nicer is to continue this magnon to the spin chain edge. So from this point of view, what you can think of is that you have some magnon which is incoming on a very, very long spin chain. It is absorbed somehow by the non-BPS operator and then spit out again by the non-BPS operator. So what is what's happening in these kinematics after we do the analytic continuation is that the weight is now given by a sum. Because we are putting two hexagons together in this picture around the non-BPS operator, when we try to put a magnon on the side here, a side that is cut into two, we have to sum over all possible ways of doing it. So the magnon can be on the first hexagon or on the second hexagon and so on. And since we have a magnon at the top and a magnon at the bottom, we get 4 possibilities, which are represented here by these 4 diagrams. Okay. Now, we should remember that the only thing that we care about here for this calculation is to actually identify the rapidity of the magnon at the bottom and the top, and also trace over the flavors. Because we don't care about the, I mean, eventually it's going to be a mirror magnon, and the flavor of the mirror magnon is not something we can observe, and so we just trace over it. And as we do that, we see that 2 processes disappear entirely. So they are proportional to transfer matrices in the vacuum, so they are 0. And the only diagrams that remains are the one in which the magnons are never standing on the same hexagon. And this is a big simplification, because then we get a very simple result for this weight, which is given by the sum of 2 terms. So each term is coming from one diagram here, and is expressed in terms of some transfer matrices again of the SU2/2 algebra. What is nice about this combination is that it's exactly what it takes to actually write down the full SU4/4 transfer matrix in terms of the SU2/2, I mean the transfer matrix of the SU2/2 subalgebra. Okay? So that was first written down by Bizert. It was, I think, an attempt to reconstruct the 4/4 an exact 4/4 transfer matrix. So here I'm not saying that this formula is valid. I mean, it's an exact formula, but it is a formula that is valid asymptotically. Okay? And but the idea is that this is clearly a big hint at the fact that this object that we are manipulating here is in fact a transfer matrix, but it's just not the one we have for the TBA, but the smallest one possible, the one for the defining representation of SU4/4. And then we could try to look at how what happens to this identification when we take into account finite size correction. And if we do so, we found, at least for the leading exponentially small correction, that this relation is still there. Okay, so the corrections are such that this relation to the transfer matrix is preserved. Okay. One could also argue that this is the most reasonable or simplest solution to a kind of a bootstrap for these form factors or for this object, because it's possible to argue, for instance, that this weight B should be regular, meaning that it should not have any singularity anywhere, which is, I mean, the simplest way of solving that is precisely to use the transfer matrix, which are regular by definition. And it should also be crossing symmetric. Say again? No, so these are solutions to Hirota equation. Yes, so they are both solutions to Hirota equation. And this is now the summary of this conjecture that we have, which is that everything can be written in terms of solution to the Hirota equation, which are big or small t's. And the only difference between the two are essentially the boundary condition or the domain on which this label A and S or representation live, which takes the form of this T hook for the big T and the L hook for the small t, for the compact transfer matrix. So this is a summary for the replacement that we want to use. And I should add that it's coming also with a prescription for integrating the double pole, because the original problem was that we have this pole. And okay, so we also have to solve it, otherwise we are in a perpetual loop of problem. And what we observe here is that the simplest possible choice, which is to essentially just shift the pole away from the contour by some I0, is doing the job. With this choice in parallel, again, we have to do it all together. And again, I think it's, I've said that before, we are assuming a particular normalization for the transfer matrix, which is the one that was introduced in this pioneering papers. So how much time do I have with the chat?
About
10 minutes, okay. So I also wanted to say that this proposal is has in it a sort of analytic continuation trick built in for excited state. And this is akin to the way, in fact, what I want to say is that we are dealing with the roots in the same way as people deal with the root in the TBA by following the work of Patrick, Roberto, and so on. And also for the generalized Leclerc-Musardo formula or the structure constant of determinant operators, which were also studied for excited state. And the key observation is that the weight have poles. So if we take this weight that we have and we go to the physical kinematics, then we find that they have pole precisely at the position of the beta roots. Okay? So the idea is that we can then take into account the effect of the beta roots by assuming that the contour of integration, which is naively for a vacuum-like contribution going along the real line here, the real mirror line. So by assuming that this contour should also include some contour integral around the roots. Okay. So that is the most natural choice to make, and it appears to be consistent also with everything we know. So it properly introduces the roots inside the formalism. So there is a few comments about the fact that, so actually, not all the weight have poles. So I've mentioned the fact that the bottom weight is a pure transfer matrix. So it's regular. It has no pole anywhere. And it's kind of satisfying to see that this bridge, this channel, this bottom channel that is very far away from the operator cannot produce actually some excited state contribution. That will be a little bit too, how to say, well, a bit strange, I would say. However, the adjacent channel can produce pole. I mean, they can produce physical correction. But we have to make a choice. So the adjacent weight, one of them will have a pole on one sheet, and the other one will have a pole on a different sheet. So we have to pick a sheet. We have to pick a choice. But whatever choice we make is irrelevant because the two are physically equivalent. So if the roots are on shell, if they satisfy the exact Bethe-Ansatz equation, then the two results are the same. So one can have a look at what it does in practice to integrate around this pole on the physical sheet. So we have this contour integral, and what happens is that so we start with infinite integrals, but okay, thanks to the form of the integron and the sort of Fermi-like repulsion, or we cannot put arbitrarily many roots on the same pole. So so what happens is that the sum truncates, and what we get is essentially just a finite sum over all the possible way of distributing the roots on the two hexagons. So for short, what we get is essentially the same thing as was obtained originally in the tailoring approach at weak coupling, which is that this physical contribution will take the form of a sum over the partitions with some weight that we've just determined. So starting from the conjecture, we can just go to this pole, read off the residue, and extract a formula like that, which is perhaps not illuminating, but which is just okay, as precise as it can be. Where this phi here is something that has to do with the shift of the Bethe-Ansatz equation, induced by the wrapping correction. So it's something that was introduced by Zoli and Romuald, and the rest is some extra contribution, which is again controlled by the y function. So we can test this formula in the IR. So we can just now go to a regime where y is small. So this is a regime where we can expand the number of wrapping. And then we will verify that this formula and this one are in total agreement with the Lusher formula that we proposed some time ago with Thiago and Shota and which was passing several tests at weak coupling and at strong coupling. So there is also a question of normalization. So if you want the structure constant to be physically normalized, we also need to design normalization factor n properly. I don't want to spend too much time on it, so it's something that is here we drew inspiration from similar results that were found for the structure constant of determinant operator of our G function that we've heard about earlier this week. And so the bottom line is that we believe and check to some extent that this normalization factor should essentially be, should be a Freedom determinant. Okay, so it should be a Freedom determinant that is built out of the, again, of the information we can read off from the TBA equation. Okay, which are y functions and suitable kernel that we need to design properly in our case, but which we can write down explicitly. So in the end, this is a full package. So we have to take this weight, we have to deform the contour, we have to add this determinant, and the claim is that with all of this done properly and together, we should capture all the wrapping correction to the structure constant here. So just a few minutes for the checks, 5 less. Okay, good. So at weak coupling, so we can do a check relatively easily by considering a certain ratio of structure constant. So this, we start with our structure constant, and then we divide by another one, which is obtained formally by taking the limit where the bridge length at the bottom, on the bottom channel, goes to infinity. Okay, so that means that the two BPS operator have a very long R charge. Okay, very long length. Sorry. So what is nice about this ratio is that because if you remember everything was factorized in the integrand, the hexagon integrand, then everything that is related to this adjacent channel or the normalization is dropping out of this ratio. Okay, so the only thing we are left with is a single sum over the bottom bridge. So it's a simplification because we get a single channel to consider. And this sum is also very nice to analyze at weak coupling because the n-Magnon integrals, for instance, while they are known to be extremely suppressed, they enter at n times n plus LB loops, which means in practice never if you don't go too high. And the first wrapping is on the other end showing up for at L plus LB plus 2 loop order. So in particular, the wrapping will dominate for low enough L. Okay, so typically, well, there is always there is a condition one must check. So this is a case for the simplest possible correlation function that we can think of, which is with 2 graviton, if you want, and the Konishi operator. In this case, the length is 2. Manifestly, we get 2 Z's, and also LB is 1 because this guy have length 2 here. And the spin, the number of derivative is 2 as well. So the 2 Magnon integrals, they will appear at 6 loops. And the wrapping will start at 5 loops, so which is 1 loop earlier. Okay. So the field theory calculation for this ratio here was done by Alessandro and Dima and Vasco and Raul a few years ago. And we also take care of subtracting what the hexagon was predicting. So they wanted to see if the hexagon was right at 5 loops, and they find that it isn't. So they find that there is a mismatch, which is relatively gentle and expressed in terms of nice zetas, but still non-zero. Okay. So this is just Riemann zeta function. So well, a posteriori now we think that it is a good thing that we have a non-zero answer because we expect wrapping to show up precisely at 5 loops. So we expect that our formula, which are now being corrected, will fix this disagreement. And I was already mentioning this check last year using the representations that we had for the weight in the bottom channel, and that was quite a pain to do the calculation using this older approach. We probably lost 6 months of our lives with Alessandro doing this, Now I should say that this is extremely straightforward. So now that we have this representation in terms of this transfer matrix, we can just ask QSC people, and they give us the answer. So in particular, the transfer matrix for the compact representation is extremely nice in terms of the Q function. It's just this sum of, it's just some bilinears in the Q function. So these are the fundamental fermionic Q function of the QSC. And then we can also get the expression perturbatively to, in principle, any loop order, at least very high loop order, by using some perturbative QSC solvers. Okay, so the problem was solved, so we don't have much to do. The only thing that is left to be done is to carry out the integral. So here there is an integral and sum. And well, in the case at hand, it's something that we can do by residue and map directly to zeta values. So there is also a test that we could not make previously because we were a bit wrong in our extrapolation, and that we can now perform perfectly, which is at strong coupling. So at strong coupling, we are dealing with a totally different type of problem. We are dealing with a string theory problem in ADS 5 times S5. So we have to find some nice minimal surface that is ending on the 3 point at the boundaries that we selected. And in principle, the problem can get very hard if we don't choose the quantum number properly. So for instance, there is this short string limit, the flat space limit that Fernando talked about, which correspond to situation where the operator have quantum numbers which are of order 1. So then the scaling dimension is large, like root of root lambda, and there is a lot of wrappings to take into account in principle. So it's a nightmare, and right now we have no idea of how to proceed. So this is a bit like the CFT limit of the TBA, if you want an analogy, and it's a very hard regime. It's well known to be very difficult to deal with. Even with the QSC, it's very hard. But there is another regime which is much nicer, which is a classical limit. So this is a limit where we'll get some smooth surface in ADS. And it corresponds to taking the quantum numbers to be of order G, okay, to be of order root lambda of the order of the string tension. And then the problem is purely geometrical. It's still a very hard problem because we get some nonlinear equation to solve in ADS, but it's a solvable classical problem, okay? And in fact, it was solved already, so we don't have to worry too much about how to proceed. And the solution is nice in the sense that it's directly written in terms of the quasi-momenta that parameterize the state at the boundary. So it's really like, give me the state, plugging the quasi-momenta in the formula, and here's the answer. It's extremely efficient. Okay. So these quasi-momenta are just the eigenvalue of the string monodromy matrix, which was introduced many years ago for the string. And where every momenta here, so there are 4 momenta for ADS5, 4 momenta for S5, and they are all function of the spectral parameter, which is the parameter to generate the higher conserved charges, of course. So the string formula is a sum of many terms. There is a real part that deal with the roots. So that one is in fact known has been known for many years to be in agreement with the sum over partition and also the Godin determinant that enter into the normalization. And there is no correction brought by wrapping at this order. So it's just the same calculation. So the mirror correction are the ones that are more interesting, and there are many of them. So they match the various mirror channels that we have in our formula. And so we can here again just focus on the simplest quantity, which is this ratio. Then the string formula is given simply by some integral over some unit circle in X space of the d logarithm, which is evaluated at the eigenvalue of omega. Okay. So that's just a very explicit formula that you can in principle evaluate numerically if you want for a given state. So now we can straightforwardly compare it with a conjecture. So It's extremely straightforward because there is this clustering method which can be used to resum the mirror series in the classical limit. So it's just telling you immediately that the log of R, the prediction for the log of R, is given by this integral, which is almost already what we want. Okay, it's almost a Li2. It's an integral of a log. And what controls the argument is what you put as a weight in your formula. Okay, so our conjecture is that if we want to be exact in wrapping, we should put these transfer matrices on the L hook that we've seen before, and then you can just calculate with this choice. So a strong coupling, the T's here are just characters of the group element omega. There is a very closed form expression for the generating function of these characters. And if you simply plug it in, you will immediately get the agreement with the string formula. Okay. So it's a very straightforward exercise to now, thanks to this formula for the transfer matrix, to do this match. And again, I want to stress that it's for this ratio, at least, it is exact in the wrapping. So there is absolutely nothing missing. So it's really a check for all the term in the wrapping expansion of this quantity. Okay, so I guess it's time to conclude. So I've shown you some conjecture for the structure constant of short operators. So it's essentially building on the idea that we can bring together this hexagon representation with the solution to the spectral problem. And here, by solution, I mean the transfer matrices that generate the conserved charges of the state of interest. In spirit, it's the same thing as the Leclerc-Musardo formula, if you are familiar with the way people construct finite volume matrix element of local operator in integrable QFT, starting from the form factor expansion. So they define something that is in infinite volume, the form factors, and they kind of convolute it with some y function, if you want, that is coming from the spectrum, from the finite volume physics. Okay. So what we are doing is kind of similar. We have our hexagons, which are infinite volume quantity, and we are combining them below an integral sign with some spectral data. Okay. The small difference here is that we find in the end that it's more useful to play with transfer matrices, or more natural in our case to use transfer matrices than the y function to parameterize the solution. So we've got a lot of evidence. There is this IR check that we can make in this Lucia expansion. We have this agreement. So we are quite confident that this is correct, or at least it's saturating everything we know right now about this problem. And on top of that, we see that it's possible to extend this conjecture kind of naturally to higher rank sectors, so operators which have other excitations than just derivatives, but also fermions, at least as long as the state is symmetric, so left-right symmetric. Otherwise, there is a problem. So, of course, there are many questions we'd like to ask, but we cannot answer, like, is there a proof, or can we make all of this a bit more convincing by completing the check to all order, etc. And possibly what will be more interesting eventually will be to explore new regimes, so to test this formula in regime like the short string limit that Fernando talked about, where we may possibly be able to match with some flat space string theory prediction. Thanks a lot.
Questions or more remarks? Please.
There have been already some formulas in the literature which expressed various limits in terms of integrals of products of Q functions. Somehow Q functions never come out in your, at least in your slides. Do you see some relation to these formulas, which might be a more general and more concise expression for?
Yes.
For 3-point functions.
Okay, so I guess that will be an extra improvement, I believe. That will be trying to get a formula which is more like in line with this separation of variables representation, which may be in practice more powerful. Although it's a matter of regime, because if you get very long operator, you get many integrals. It can be very hard to carry out these integrals. But anyway, yeah, we are at the T level, yes? We are. So now you want us to go to the Q level. And, but I believe there is something non-trivial happening. To go from one to the other, you have to resum with this mirror correction.
It's already quite an impressive step
Yeah,
from,
so the
from Y
last
to
step,
T.
The last step is probably the one that matters, but we don't know how to take it. So we have to stop at the T ground.
Thanks.
What about applications to fishnet theory, where maybe you could try to prove your conjecture, and also maybe you could try, for example, to reproduce some exact results for structure constants? There is exact prediction for length 2 operator, heavy, light.
Yeah, so that's a very good.
That could give some potentially useful information also for super young mills.
Yeah, so there is some possible reduction of this formula to the fishnet theory for certain type of operators, not every operators. Well, not every configuration of structure constant, sorry. And there I agree. So that will be interesting because the formula should just read the same. One just need to replace the T by and the Q by the relevant solution, which is also known. And one could also play with the vacuum state, which is often nicer in practice. But again, in the end, we'll get this infinite sum of integrals, and what is lacking at the moment is a way to deal with them. So most presumably to match this exact formula that you mentioned, we'll have to carry out these integrals, and I don't have any clue right now about how to do it. So.
Thanks.
Do you understand how to deform hexagons for 4-point functions of 20 prime?
Say again?
So if you consider a 4-point function of, say, of some short operators, for instance, 20 prime.
Yes.
You can write it as a sum of hexagons. Do you understand how to deform them to take into account all wrapping corrections?
Okay, so if you are, strictly speaking, interested in 20 prime, which are protected state, then the belief is that there is no wrapping issue. So there will be no divergences, because you cannot wrap anything around the protected state, thanks to supersymmetry. Or put differently, the hexagon preserves enough supersymmetry to protect the insertion of this operator. So the formula that were written by people playing with the hexagonalization of 4-point function should in principle be okay as written. It's a bit of a miracle. It's because you have protected state. But if you want to do something that has Konishi also as a puncture, then you get the problem. And I'm not saying we can infer the solution starting from what we have. And there is probably a link, but it's not immediately clear that it's solving the problem for any Riemann surface. I mean, sorry, any puncture sphere.
But, so you mean that using asymptotic hexagons, you can compute the 4-point function exactly as a formal sum?
Asymptotic expansion, hexagon asymptotic expansion for protected operators, 4-point function of protected operators is expected to be complete. There is some assumptions that people had to make about some loops. So there are some bad loops again in this construction, but they are expected to be just 0 thanks to supersymmetry. So I mean, modulo some reasonable assumptions that have been defended by some people, it should be complete.
Thanks for the nice talk. Great to see that integrability gods can be kind sometimes. So technical question. So you have this W left and right, and you have plus minus distributed between them. So is there any intuition why like the 3 cuts, like 2 plus 1 and 1 plus 2 in another case?
So the question is why is 1 plus and the other minus?
Yeah, because they will have different cut structure, for example, right? And
they have the same cut structure, just that there is one that is nice to cross in the lower half plane and the other one that is nice to cross in the upper half plane. Yes.
Or, okay. In the long cuts, I think they would have finitely many cuts, right? And then one would have...
I cannot hear you. Can you?
In the long cut version,
Yes.
they would have like 3 cuts, I would say.
They have the same cut structure, you agree? It's just
Okay.
one is a complex conjugate of the other.
And then, so when you sum in mirror channel, well, that's not related probably to this particular work. Why do you have only, do those have to sum over other polarizations, not just, you know, so there could be many auxiliary magnets and stuff like that. So is it all drops out somehow?
I did not understand.
So in the mirror channel,
Yes.
so states in principle, they're parameterized by magnets of many types.
Yeah.
With non-trivial polarizations. Do you need to consider those in the sum integral?
What is the polarization? You mean the flavor?
No, when you glue together two hexagons, right? You have the sum and integral.
Yeah, I have a sum of integrals, yes.
So why are they only parameterized by A? Because, I mean, in principle, states in the mirror channel, they could also have some non-trivial polarizations.
So the state, we are summing over every state in the mirror channel. We are summing over all the states in the mirror channel. There is nothing missing here. So if by polarization you mean flavor, they are already taken care of.
But the kernel would be the same no matter what the flavor is, so it's just with one index A.
What we are finding is that the flavor only enter in the transfer matrix. So the rest is more like, yeah, the rest is flavor independent.
All right, let's discuss later.
We have an online question. But previously, actually, we experienced some problem with bots. So maybe it's a bot, we will see. So Cyberstein, 1981 is asking. Maybe it's an AI, you will see. Why is it challenging to extend your proposal in higher rank sectors that are not left-right symmetric? Is it related to the derivation of the bottom weight?
The derivation of the?
Of the bottom weight.
Well, it's not unrelated, but so in fact what was found asymptotically using hexagon is that structure constants are 0 if the states are not left-right symmetric. So if you just blindly apply hexagon construction to higher rank structure constants, then you will see it's like a super selection rule, not super selection rule, selection rule, yes. So it's identifying the left and right wave function, or it's 0. And we are starting from asymptotic solution, asymptotic hexagon, and we are trying to correct it. So the question is, how do we correct 0? And I don't know. So, but most likely we cannot just play this game. So there is these transfer matrices that I'm using. Actually, you could ask, are they left or right wing transfer matrices? And the answer is, does not matter because they are the same, because the states are left-right symmetric. But as soon as you lift this symmetry, then you have to decide, I mean, are there transfer matrices on the right, are they on the left? How do you do if the state is not symmetric? And the answer does not look very consistent then.
Maybe it's a bit similar how in excited state TBA usually got P equals 0 sector, and then when you would like to conjecture what is the excited state TBA of a moving particle, then you have to plug in some extra input. Yeah.
Yeah. I want to believe that they're actually 0, exactly 0. But I cannot prove it. It's just.
I also have another question. So going back to this missing weight, what you said, yeah. So it's still a bit confusing to me because didn't you say that you are calculating a 3-point function BPS, BPS, non-BPS? And now you are putting an excitation on the BPS guy, no?
Yeah, so I'm pulling out a mirror magnon and I'm moving it to the where there is some space left, which is this BPS.
So it's like an excited state Leclerc-Musardo formula?
Yes.
Okay.
It's just that there is a relation between the two. So the weight we are trying to calculate is an analytic continuation of this diagonal.
So then you can dress your formula from BPS, BPS, non-BPS to excited state BPS. No, same guy.
Possibly we can go to more complicated situation. If it is diagonal, possibly
Yes, yes.
Yeah. Yeah. Although I will not dare adventuring myself that far, but yeah.
Okay, thank you.
Hi. So, Benjamin.
Sorry.
Okay, I have two questions actually. The first one is, if I understand correctly, that what you find can be extended to gamma deformed theory, and in that case you will have to replace with a gamma deformed transfer matrix, and therefore get these corrections also for those states, such as some BPS states in the original theory that start to get wrapping corrections. And I ask this in connection to the fact that people want to check things in fishnet theory, for example. Is it the case that your findings will survive with this minor modification?
There is a reduction of this formula to certain three-point function in the fishnet theory. I'm not talking about gamma deform in general. I haven't think about it. I haven't thought about it. But for the fishnet theory, yes, it's possible. You would have to take one BMN vacuum and two open string state with no wheels correction.
Yes, but yeah, I was asking about gamma deformation because it would be probably interesting to see those states that are protected into the n=4 theory, and they are not protected anymore once the theory gets gamma deformed, such as trace of x to the 3, for example.
Yeah, so you have to enforce this protection by hand, okay, so somehow. That's why I was telling you for the fishnet theory, the rule of the game is that you may be able to apply this formula to situations where two of the states are protected. So for that, you need to open up you need to cut open the trace and consider this open spin chain state, yes? So otherwise, if you get wheels everywhere, this is not going to work.
Okay, and the second question is, since now you have full control over the mirror integrals around an operator which gets wrapping correction, if you would expect that in some null kinematics, for example, when you have 4 points connected by null contour, still you have factorization of into disk correlators. And I'm asking this because if I remember correctly, it is the case for the length 2 Konishi from Korchemsky, Eden, Sokachev, Maldacena. Do you still expect this to be true for, like, say, length 3, 4, and so on, short operators?
I don't know. I don't have expectation.
Okay.
Benjamin, can you show us the last transparency with the formula?
This one?
No, with a formula. The last formula.
The last what?
Before.
the
Yes. So this integral you wrote is formally it is the functional determinant of the spectral curve. So this is correct when you have infinitely, well, very large charges at the operators. Do you think that somehow this formula can survive for finite charges?
So this is for finite charge. This is including all wrappings.
Ah, I thought it was the strong coupling approximation. So it is a functional determinant of the spectral curve.
It is your formula, but in your formula you get a product from 1 to 2. and we extended it to 4.
Very good. So
that's it.
So you found the interpretation of the 3-point function in terms of the
Well,
operator of the
interpretation, I
spectral
don't know
curve.
if it's interpretation. Okay, you're right that it's associated to, it has this interpretation, this functional, but I don't know, I don't know what it means.
Thanks, it's nice.
Okay, so I think it is time to thank for all the speakers in this morning. And don't forget the conference dinner. How to get there, you can find on the conference